font. So before we get into this next part of FQL, I want to talk about something in database management systems that is extremely powerful idea, and I would also say surprisingly simple for how powerful it is. And it's something that we're used to already. So what is indexing in as far as databases are concerned? It's actually very similar to what we're used to as an index at the back of a textbook. So I think that's a good analogy. Think about the index at the back of a textbook. It contains, let's just say, which contains sort of, we'll call them values, like Charles' Law, if this were a chemistry textbook. And those are lookup words. So those are kind of like keys. And these lookup words point to indexes. And those are page numbers, right? So this allows us to find content in our textbook very, very quickly. If otherwise I needed to figure out where Charles' Law was referenced in a textbook of hundreds and hundreds of pages, I would just have to flip through it. So it's very, very inefficient. And indexing gives us a way of making that much faster. And that's the idea. So an index in general, but in databases in particular, which is what we're going to be talking about, it allows us, or I guess allows certain queries to be executed more quickly. It's all about time efficiency. Another thing to note that's really important, though, is that this index is a separate data structure. Like, it needs to be maintained. So it needs to be stored in parallel with all the tables and rows, but still separate from them. And that means that the index that we've got not only needs to be created, like when we first create this textbook, it needs to have, like, that wasn't a built-in part of the textbook, somebody needed to go through and create that thing. And that's the same with our indexing in databases. But one important thing is only once. The index needs to be created, but only once. And then any future queries that we make, which can use it, I guess, can be significantly faster. And by significantly, we really do mean something pretty impressive, depending on what happens. And before we go a little further, let's just look at an example over here. So here's the database we've all been working with, but now in a numbers format so that we can look at it visually. Here's the movies table. And over here we've got these, all the rows listed out here. And if I wanted to find all of the movies that match the year 1995, or let's come up with something interesting, maybe 1989, I'd have to go through and say, does this match? No, does this match? No, does this match? I'd have to go through all of them. And eventually I would find The Little Mermaid, and I would find UHF, and maybe there's some others in there that I didn't catch by scanning. But either way, we'd have to go through all of them and figure it out. Now, if instead, and if we do that over and over again, that's kind of slow. If instead we knew we were going to query by year, we could create this kind of index table over here. And it's indexed by a particular column, notice. So we would have to create an index table just for the year. And then over here, we could look up, so notice that 1986 has 0. That means ID 0 appears for 1986. But something like 1999 has 4 things, 7, 17, 22, and 32. 7, 17, 22, and 32. Cool. So that's the idea. It's almost like a reverse lookup table. So this has the actual information. And in this lookup table, what used to be values are keys. And what used to be keys, like IDs, are values. So if we wanted to find 1989 here, we would jump to the 1989 key, wherever that is. Oh, it looks like it's incorrect, actually. It lists just one thing, 34. So that's an inconsistency in our index, which is something we could talk about, actually. But it should have more data in there. So that's the kind of speed up we can get. We can just jump to that one row if we're looking for 1989. And to make this maybe a little more salient, we could imagine not just 36 rows, but if we had like the actors table that has almost 2,000 rows in it. Let's say we were looking for all actors whose first name was, let's go with Kirk. all actors whose first name is Kirk in our database, in this table. We could do this, right? It would take us another probably 5 minutes to skim through all these and find them. But there would be a better way. If we knew that we were going to make that query over and over again, we could make one index table off to the right here that was keyed by first name, so that it would contain Kirk, and it would tell us, oh, that's in row 58 and 111 and 5 and 1,309. And then we could quickly jump to those 3 rows, just get those 3 rows, and leave. That's the idea of an index. Any questions about it?
Sorry.
Yeah.
At what point are these indexes created?
Great question. Yeah, that's up to us. And if we look at the specs, there's going to be a method that you'll be asked to implement called add index table. So the idea is if we take movie table and say add index table for year, then at that point in time, the index will be created and no sooner. Okay. So it will be something that the database user has to opt into.
Okay.
And to create that, to add that index, we're going to need to choose a table, the index, and a column to index by. And that's important. Like, we're not going to index by everything, just a particular column. And what we do then is we create what we can call an index table. And what there is something where we store every row value for that column as a key, and that row's primary key as a value. I'll say what that means. I'll give you an exact example in a second. Was there a question? Okay, let's look at an example. Like in the workshop, this is what an index table will look like when we're asked to make it. So if we add an index table for year and then retrieve that index table, that is going to be an object where the keys are year values, like 1972. And the values are primary keys. And it's an array of row IDs.
Okay.
Cool. So that's to create it. There's actually some other things to consider, though, because creating it is one step, but now we also need to use it. So to use an index, in our querying, we need to detect whether any criteria, so this is related to where, I'll write that in here. So this is for where. Match any index tables that we have. That's the plan. So if we notice that somebody is querying for year 1992, oh, and we have a year index table, then that means we should start our query by limiting our search to just those entries that match our index table. So if we know that we're searching for year 1992, and that's one of the criteria that we've got, then we start off by saying, wait, we don't need to look through all the rows. We just need to look through the rows that match, that are stored in this particular index table. So our starting set of row IDs might just be this array here, if we know we're searching for year 1992.
And when we create these index tables, do we have to persist them? I mean,
yeah, that's a great question. Part 3, that's fantastic, because in theory we should, right? Because it's expensive to create them. We have to loop down everything. And that's not in the purview of part 3. Part 3 doesn't assert that you make sure that those index tables persist, but I'm pretty sure that is covered in part 4, if I remember correctly. Part 4 has a lot of random stuff to it, but it is totally and completely non-mandatory. Part 4 is just a bonus thing. But for now, let's not worry about persisting the index tables. But it's a great question. Well, now, yeah.
No, I was thinking that if we had to, like, if we created indexes and persisted them to files and have to read, like, and then, because based on explanation, given a query that contains a where, we should check if the where columns have been indexed. And if they have been indexed, then we have to go read the index files, then get, do some, I mean, all that process, how is that faster than actually just going and searching through the
Yeah, no, that's a great question. In fact, I want to bring up something, a counterexample of when indexing can actually be bad, and that plays into it. Let's use our first name example again with Kirk. The whole point of an index table is that it's going to be fast to look up the first name in the index table. So, like, let's say we have an index table of all first names followed by all IDs. So that will show us that Kirk. Okay, cool. We can quickly find Kirk in our index table, and then we can quickly find the following, 3 IDs. Then we just need to loop through 3 things and do 3 different gets, 3 different reads, reading from specific rows, specific, in our case, files. So that altogether, that was like 4 to 5 read operations, as it were, to get through all of those things. One, we had to read from the index table to get and to see whether it had that. So one, we had to see whether you had that index table. If we did, 2, we had to then read from that index table to get the array of row IDs. And then we had to do 3 separate reads, potentially, for the 3 different rows. So that was 5 in this example, row ID reads that we do, as opposed to about 2,000. That's sort of the trade-off. And it absolutely relies on it being fast to search our index table by a given first name. Cool. Good question. So indexing is really cool. I think this is amazing. This is a really cool thing to understand. And I would actually say that it separates sort of novice database users from intermediate database users. Or maybe advanced database users, honestly. I don't know. And it can be challenging, honestly, to use. It's not like it's like super easy. But I would say that the core concept is not terribly complicated. This core idea of, like an index at the back of the book. So executing it well, it can be hard. And what I want to mention with that is that you will not need, or how do I say this? Knowing how to implement indexing, i.e. being a database developer, like being somebody who is creating a database management system, is not important. Like, that's not a thing that you need to be able to do, right? Somebody's already done this. Postgres has already figured out indexing, and indexing is a thing that all the different database management systems that I know of out there have. So knowing how to implement indexing, knowing how to build it from the inside and how it all works on the inside, that's not super important. But knowing that it exists and what it means, that's really, really powerful. So this is a tough part of the workshop if and when you get to part 3. So I'm saying this because I don't want you to hold yourself to the standard of, oh, I'm having trouble getting through this indexing. That's not great. Really, I think it's more important to focus on the concept and how we can use it than how we can implement it. But before we do that, and before you go any further, I do want to talk about, on the other hand kind of thing, or really also, I really should just say, like sort of additionally, indexing does have downsides. What are some of those downsides?
Well, my first thought was that you would have potentially a lot of different indexes for one database.
Absolutely. Every index table you include adds space, right? Like, this takes up literally another table, like in the back of your textbook or in your database or wherever it is. That space or memory or storage or whatever you want to call it. So every index table you include adds that. And there's something else too, which is also when updating tables. So that could be updating a row, it could be inserting, it could be deleting. So those operations. You will also need to make sure, you will also need to update any, and that could be many, relevant index tables, right? If suddenly I change the year of this movie from 1986 to 1988, I not only need to change here, I need to change my index table now because I have an index table by year. So that's kind of tricky. That's going to cost, right? It costs extra time on each update. And in some sense, it also has the, it will cost sort of extra mental effort, we'll call it, for developers who are working on this, right? So this is not super relevant to people who are using databases, but like if you're a database management system developer, this is relevant to you. Because like if you need to implement indexing, it's trickier. And that's worth thinking about. It's making the system and the software more complicated. And that's always a trade-off worth considering. The other thing is that it's not only, and this last one is interesting, and it relates to something that Ike brought up. This is not always good. It can actually be worse. It can make things worse for homogeneous rows. And by worse, I mean slower. So let me replace that. Can make things slower. Indexing can actually slow down queries in certain pathological examples, and we actually have a pretty good one over in this actors table. So in the database that we scraped from, there was a gender column, and I think it had entries for M or F. Maybe it allowed for U. I don't remember if it was progressive enough for that, but that's the database thing we scraped. And that means that if, let's say it has just M or F, because I don't think it has U in here. That means that if we were to index by gender, we would be left with an index table that has two keys, M, which has roughly 1,000, and F, which has roughly 1,000 entries. And not only is that at least as slow as going down everything, it's actually a little bit worse because we have to go, let's say we want to say, find all of the people with gender M. Then we would read from our index table. Well, that's one read. Now we would need to read all 1,000 of the entries for M into that index table. That's another 1,000 reads. We need to loop down that and do another 1,000 reads on the main table. So at this point, we've already done 2,000 row reads, just getting through this, which is no better than when we started. So for homogeneous data or homogeneous rows, indexing can actually make your querying slower. So it is something to consider. It's not better in all cases. Oh, and you know what else I wanted to add about indexing? Not for this workshop, but in general, there are different kinds of indexes. Yeah, and that's cool to know. That's a really cool thing to know. Two common types, and this first one is what we're going to be doing in the workshop. This is hashed indexes. This is what it's sometimes called. So yeah, this is what is in the workshop. This is the idea that we have like an object where the keys are, you know, year values, and the values are arrays of primary keys, arrays of row IDs. But another really common type are sorted indexes. Yeah, so sorted indexes are actually much more common. And a sorted index is something like, I mean, honestly, for year, we probably should have a sorted index, really, where we say have some binary search tree instead of some hash table-like thing. Have some binary search tree where we've got everything, all the year keys sorted somehow in this binary search tree. That allows us to do a lot of interesting things. So not only is it still going to be much faster than our ordinary table scan, so it'll still be like, it'll be log n time, which is very fast to find one of those keys, but it allows us to find ranges of values. Like if we wanted to find all the movies made between 1970 and 1980, we could find the left part of that, 1970, the right part of that, 1980, and then traverse between them and get all of that. With a hashed index, since they're not sorted by anything, it might be tough to do that. We'd have to say, I guess years are a bad example because we could just do 1970, then 1971, then 1972, et cetera. But you can imagine if we had a continuous value like rank, maybe. That would be tough because we can't just say, hey, I want everything between rank 7 and 8, And if there are arbitrary decimal points, then we have to do like 7.00001, 7.00002, 7.00003 with a hashed index, right? We just have to keep looking up and incrementing. But with a sorted index, we could just find the left side of the range, the right side of the range, and everything that goes between them. So sorted indexes are incredibly common and much more common than hashed indexes out there. But I would say that in terms of implementation and us getting used to what an index looks like from the inside, hashed indexes are a little bit easier to grasp and work with. Any other questions about indexing? Great. So just a reiteration that this workshop in general is not it's not a linchpin of your success or anything. This is a workshop to practice JavaScript. This is a workshop to understand some cool things about database management systems. But at the end of the day, you will not need to implement a database management system to succeed as a web developer, because so many people have already done it. And so really, at the end of the day, you want to know how to work with existing database management systems. This is a fun exercise to reverse engineer and see it from the inside.